So today we learned about a new kind of function, something you probably have no concept of. And everything we've done up to now has been, linear, polynomial kind of stuff that you have dealt with before. I mean, even the chapter on radical functions, you've done square roots. It's not like we had to tell you what a square root was. But a logarithm is something that is kind of new. And there's a reason why we learn it right now, because it turns out the logarithm is the inverse of an exponential, right? That's why we learn about inverses right before we learn about these two things. So most of these, I didn't even copy all the objectives because it runs off the page, but most of these have to do with understanding that fact. Logarithms, exponentials, inverses of each other. And then of course, you gotta be able to recognize what the graph of a logarithm looks like and how to move it around. And the thing is, the way you move it around, it's the same way you move around any function, like the ones we just looked at in the homework. All the shifts work the same. So logarithms. Come on. Boom. Okay, so we did this graph last class. F of x equals 2 to the x. Right, this was our table of values. This is what the graph looked like. It had an asymptote on the x-axis, meaning it gets close to the x-axis, but it can never touch. There's nothing you could ever plug in for x that would make the y equal 0. So that's why we have this thing called an asymptote. It has a y-intercept when x is 0, then y is 1. So you see where it crosses right there. In fact, we could add something else. The domain is all real numbers, goes side to side. The range is y greater than 0. There's no y coordinates less than 0. Not even 0 is allowed. Okay, now, how do you take a table of values and make the inverse? You just switch the x's and the y's, right? Right, take all of these points here and flip them. So that's what this is right here. So this is f to the minus 1 of x. Now, if I graph those, right, graph these points right there, and then connect them with a line, that's what it looks like. And it should look like it's a flip across a line, right?
Thank you.
All right, thank you. Do you remember which line it's a flip around? Remember, all inverses should look like they are flips across the line y equals x. Like this line right here. If you tilt your head, it should look like this is a line of symmetry, geometry term, right, for these two graphs. Exactly the opposite. Or exactly like the reflection across that line. So this is the f of x, 2 to the x. This is the f to the minus 1 of x. Okay, so here's the point where we state that, in fact, that function is log, what you would say, log base 2 of x. Right? So the inverse functions are 2 to the x, exponential, log base 2 of x, logarithm. Don't write that down. Okay. So the log, the LOG, stands for logarithm. That's how you spell it. There's no vowel in between the TH and the M. Logarithm.
Excuse this interruption. At this time, please release all SOL testers to the test site. Please release all SOL testers at this time. Thank you.
So this is the graph of the parent function, logarithmic function. Y equals, in this case, it's log base 2 of x, right? The general, you would just say log base b. It could be, b can be any number greater, just like with exponents. It could be any number greater than 0, not equal to 1. Okay. And because we flipped everything on the exponential graph to create this graph, where the exponential had an asymptote of the x-axis, the logarithm has an asymptote of the y-axis. Right? This graph can come infinitely close to the y-axis, but it can never touch it. There'll always be some space in between those two, and it goes forever down. Right? It does not stop. There's arrows on both sides of this. So remember, when you make an inverse, it flips the x's and the y's. In effect, that flips the domain and the range. So if we go back to what we say, the domain of an exponential is all real numbers. That means the range of a logarithm is all real numbers. If you're looking at it on the graph, if you put it in the calculator, and calculators do not handle logarithms very well, it kind of looks like it's leveling off, like it's not going up forever, but it is going up forever. Has to, because it's the inverse of an exponential, and the domain of an exponential is all real numbers. Right. Remember, for the exponential, it was only above the middle, meant the range was y greater than 0. That means the domain of a logarithm is x greater than 0, which is kind of important, because up till now, what did we say were the two situations that limit the domain? Divide by 0, square root of a negative. Okay, now we've got another one. If you got a logarithmic function, you can't take the logarithm of a negative number. You can't take the logarithm of 0 even, right? Because it never touches the y-axis. X cannot equal 0. That's an asymptote. So logarithms have a limited domain. Okay, whereas the exponential had a y-intercept of 1, the logarithm has an x-intercept of 1. So here's how, one of the things that we're supposed to be able to do for the SOL is to convert from a exponential form to a logarithmic form. And they're essentially, exponentials and logarithms are different ways of representing a relationship between the same set of numbers. So to say 2 to the third equals 8, which we all know, 2 times 2 times 2 is 8, that's the same thing as saying log base 2 of 8 equals 3. I mean, essentially, if you don't have, if you don't know the 3 there, if you're just looking at the logarithm, what you're saying to yourself is, what power would I raise 2 to get 8? And the answer is 3. So notice the base of the exponential is the base of the logarithm. Right? The logarithm equals what in the exponential was the exponent. Which tells you that logarithms are exponents, right? Logarithms are exponents. That's what they are. That's important. That's why they were developed in the first place. So we should be able to, given an exponential relationship, write it as a logarithm. Or given a logarithm, write it as an exponential. They're not asking you to solve anything. They're just saying rearrange the numbers and rewrite it, just like that. We good? Allie? Okay. So how would I rewrite this one? You got the example on top. How could we rewrite 4 squared equals 16 as a logarithm? What would the base of the logarithm be? 4, right? And the base of the exponential is the base of the logarithm. So since that's a 4, that's a 4. Okay? What is it that goes inside the logarithm? 16. Again, the way you're asking yourself, just looking at log base 4 is 16. What power would you raise 4 to get 16? 2. That's it. Okay, try to do this the reverse. Here's a logarithm. Rewrite it as an exponential. What will be the base of the exponential? What's the base? Taylor? 3, right? You're going to take that. That's the base. Okay. What is the exponent? 4. The logarithm equals the exponent equals 81. That's logarithms, exponentials. So converting exponentials to logarithms or logarithms to exponentials, the basic pattern is like this. You can start with an exponential, which is y equals b to the x. Then you rewrite it, log base b of y equals x. That's just in general, right? Not just sort of giving you one example, but this is the pattern that you use. So given that, this would be the first you tries, okay? Things that you're going to hand this in at the end. So please do it. Okay, you try. Rewrite as a logarithm. 1 equals b to the 0. What did you write as the base? Brianna? What is the base of the logarithm? It's b. Whatever the base of the exponential is, it's that. Okay? What goes in the logarithm? The 1. Oops. Equals 0. Okay. Which, you know, this one on the left, that is Anything to the 0 power equals 1. That's what that's telling you. Anything to the 0 power is 1. That the same thing is the log of any base of 1 equals 0. It doesn't matter what the base is, the log of 1 equals 0, which is just telling you the x-intercept, the point 1 comma 0. Okay, try this one. Convert a logarithm back to an exponent. What was the base of the exponential? 5, right? 5. 5 to the what power? 4, right? The logarithm equals the exponent equals 625. Okay, so that's converting one to the other. There's always a few questions like that, and they shouldn't be hard, right? It should be fairly easy to do that. I mean, one thing, well, we'll talk about that in a minute. So here's a little history for you. Logarithms were invented in about 1609. Logarithms were invented. Okay, they were invented by a guy named John Napier. And the thing about it is, because logarithms equals exponents, then you can use properties of exponents when you're dealing with logarithms. Okay, which means, remember, this property of exponents, if you're multiplying a to the m times a to the n, the way you simplify it is by adding the exponents. Right? That's a property of exponents that we already know. Right? So, in effect, we're changing a multiplication into an addition. And that's why logarithms were invented. Because in those days, calculations were really hard. You didn't have computers or calculators or any kind of technology to do any of this stuff. You know, adding is something that you can do pretty easily by hand. Multiplying is something that you can't. Okay. Now, at that time, that 1609 is not that long after a telescope was invented. And it's, you know, in between the time when Copernicus says the sun's the center of the universe, and Galileo kind of says, yeah, he's right about that, and gets put in house arrest for the rest of his life. Galileo, using his telescope, he didn't invent the telescope, but he made his own. He was actually living and working at a place called Padova in Italy, which is close to where my wife's family is from. And he was looking, and he was able to see Jupiter. And Jupiter has got moons that are going around it. He could see that. You know, for the first time, people could look up there and see that clearly there's these things that are going around Jupiter. They're not going around the Earth. And so that's when he kind of said, all right, let's just give up the fiction that the Earth is the center of all of this. The sun is really the center. There's lots of things that orbit, right, that are not orbiting around the Earth. So that all came about. That's what happened then. Okay, but they couldn't do much for the calculations until they got this to come along. And it's only because of things like the telescope and logarithms that they're able to calculate a lot of the relationships that exist in the solar system. For example, you might say that the Earth goes around the sun, but is it going around the sun in a circle? I mean, is it just like that, a perfect circle? And the answer is no, it's not. It's actually an ellipse. Right? It's like an oval. It's just a little bit longer in one direction than the other. And the only way they could know that was the calculations that they could do with logarithms. I mean, just think the distance from the Earth to the sun is like 1.5 times 10 to the 11th, right? And that's rounding off, you know, 1, 5, and 10 more zeros after that. And imagine trying to do a pi r squared calculation. Very, very difficult in those days. But if you could, you know, calculate the exponents of that number and then just add the exponents, now you've got the calculation. So is a guy named Kepler that in about the first 100 years after logarithms that came up with some of those pretty precise orbits that we understand today. Okay. Now, if it was just about calculating things, we would say, why do we need that? We do have calculators now. We do have computers. Don't need them anymore. But the truth is that it's a function. Logarithmic functions occur, right? They do occur. And there are things that we need for modeling sometimes. There are things that come up naturally when you're solving calculus problems that don't even have logarithms in them. All of a sudden they appear. So we do need logarithms, not just for the calculating anymore, but just in basic math, it's part of it. Now there's two special logarithms. Right? The log base 10 of x is called the common logarithm. That's the first one. The guy John Napier, when he did logarithms, it was a log base 10. Essentially what he did is he made a table which gave you, for many, 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 many numbers, whatever the power would be, you would raise 10 to get that number. Right? So for log base 10, you would look in this table and you'd say, oh, I want to do a calculation with 550 in it. Right? And so you would find in the table what exponent you would have to give 10 to make 550. That's the logarithm, the exponent. So that was the common logarithm. Now, common logarithms are so common that usually we don't even write the 10. Right? If you see log x, that means log base 10. If you look at your calculator, right, there's the log. That's log base 10. Okay. Now, the other special logarithm is log base e of x. Now, e is something that we haven't encountered before. I don't think we've encountered it in this class. Maybe you encountered it in a different class. But e is like pi. It's irrational number. It's a decimal that never terminates and it never repeats itself. Okay. If you look in your calculator, you've got e on there. You've got e, and I can't see on this one, but where do you see the pi? Pi is on the divide. Let me see on yours. Yeah. If you look above the divide, you see the little e that you got to get to with the second. Right? So if I go like this, right, second, and there. That's that e, which is in the logarithm over there. If you hit enter, you can kind of see what the value is. 2.71828, right? Like I say, it's a decimal. It never repeats itself, and it never terminates. That's what e is. And that is called the natural logarithm. A log base e is called the natural logarithm. And it's actually written like this. Y equals ln of x. Right? ln means log base e. Right? If you look on your calculator, what do you see right below the log button? ln. Okay, so that's the natural log. And I can tell you that in science and math, when somebody says logarithm, that's almost always what they mean. They don't mean any other log. ln is really the one. When people say log, then they mean, you know what they mean. It means ln. ln is the one we use in math and science. I mean, there are examples of log base 10s. I mean, if you look in the book, always at this point, when they give an example of a log base 10, it'll always be like earthquakes. Earthquakes are measured on a scale, which is log base 10. So a log, if it says the earthquake on the Richter scale was 5.0 or 6.0, That's an exponent, 10 to the 5th, 10 to the 6th. That's what they're giving you. So, I mean, that's an example of using a log-based 10 in science. But most of the time, ln is the one that we're using. So, evaluating logarithms. Right, so log base 2 of 16. I mean, like I said, some of these are simple enough to solve just by, say to yourself, what power would I raise 2 to get 16? How many times would I have to multiply 2 together to get 16? 2 times 2 times 2 times how many 2's? 4 times. So the answer is 4. Okay. However, I mean, this is the general way, because they're not always that easy to solve like that. Usually the way you evaluate a logarithm is you do this. Set it equal to x, and then convert it to an exponential. Okay, well, we've done that already. How would I convert that to an exponential? What's the base of the exponential? 2. 2, what's the exponent? X equals 16. Right? You change it into an exponential. And when you get these problems in our beginning math book like ours, most of the time it should be kind of obvious that both sides could be represented as powers of the same smaller number, like 2 to the x, and then you should say, okay, well, 16, that could probably be represented as 2 to a power. What power is it? How about 2 to the 4th? So now, if you have an equation that says 2 to the x equals 2 to the 4th, what do you think x equals? Right? If the left equals the right and the bases are the same, then the exponents have to be the same. So x equals 4. I think the next one is a U-try, where you're going to try to do the same thing. So remember, set it equal to x, convert to an exponential. Who's got an answer? Anybody? Deshaun? What is the exponential? Okay, so first you did that, then you made it 8 to the x equals 8. Right, so if 8 to the x equals 8, the 8's are the same, so the exponents have to be the same. What's the exponent on the 8 on the right-hand side? 1. That's 8 to the 1. 8 to the 1. So x equals 1. Got pass? Cody? Do you have pass? Go to attendance. Oh, come on. It's not that cold. That'll be a referral. Okay. Okay, so that's that. Now, let's say you got a log base 10 or an ln. You've got that on your calculator, right? If you're asked for a log base 10 or an ln, then by all means, put it in the calculator. Right? Just try the log of 34. One 1.53 something something. I'll just make it 1.53. Okay, try a ln of 23. .14-ish. Right, so if you've got a log base 10, an ln, these things are easy. But the thing is, there are properties of logarithms that come after this that allow us to change a logarithm of any base to log base 10 or ln, if that's what you wanted to do. And we used to spend a lot of time with that. It's just that nowadays, the calculators will actually do the logarithms of any base anyways. It may not be right there, logarithm and ln, right on the front, but you can take the logarithm of any base using the calculator. And this is how you do it. You go math, and then scroll to the bottom, and you see the log base. That'll let you do logarithm of any base. There's no reason to do what we call change of base formulas anymore. And that's one of the reasons why in this class, we always use the 84s. The 83s didn't do this. Right? The 83s didn't do this. I mean, in the end, we weren't able to graph logarithms unless they were log base 10 or ln before, because we couldn't do the calculations. We always had to do the exponential and then switch all the x's and the y's. That was our best way. Well, now you don't have to do that. You just use the log base and you can graph anything, or you can do any calculation. So if we go to those two that we did already, let's just see how they would have worked if you'd have done log base instead. Right? Arrow up. Log base. Right? There's log. It's giving you a place to put the base. It's actually blinking on that. That is 2. You got to arrow out of that to get to the 16. What did we say was the answer to that one? It was 4. 4. Right? So you can do calculations of other bases. Just know where the log base is. And how about log base 8 of 8? What did we say that one was? and 1. That was what we got for that. So evaluating logarithms, you have a calculator for that, right? Don't really worry about it. If you look in the book, I mean, you can't do that at home without that calculator. So if you don't finish it in class, then by all means, do the way where we solve it. Set it equal to x, convert to an exponential. You should be able to solve it. Okay, the last thing is, again, now we know what the basic shape of a logarithm graph is. We should be able to move it around and stretch it and compress it and flip it and all the same things that we've done to all the other kinds of functions. And this chart is just it summarizes all those things that we already know how to do. Right? If you multiply by a number, if that number is bigger than 1, it's a stretch. Right? If the number is less than 1, it's a compression. If the number is less than 0, it's a flip. Right? If you add or subtract inside, that's a horizontal shift. Minus means right, plus means left. If you add or subtract a number after the function, plus means up, minus means down. So put it all together. And that could be, in fact, a lot of times it be presented like this. Y equals A times F of X minus H plus K. I mean, because it could be any function. That could be absolute value, quadratic, anything. So, example. How does the graph of log base 4 of x minus 3 plus 4 compare to the graph of the parent function? Well, what would be the parent function of that? If you take away all the shifts in it, what's left? Right? Parent function is just it's got the log base 4. There's got to be a base there. So the log base 4. Okay. Now, what is the minus 3 going to do to that graph? Right 3. And what about the plus 4? Up 4. Right. This could just as well have been homework that we did with exponentials or square roots, right? All of them in this testable unit kind of. Now, here's the thing about if you are just a slave to the calculator and you don't know anything else except for what you put in the calculator, you're going to have problems with logarithms because the calculator doesn't deal with logarithms very easily. And I'll show you why in a second. Right. This is the graph. This blue line here, that's the graph of log base 4 of x minus 3 plus 4. Right. It's got the shape that we expect. Right. It has an asymptote. It's not anymore at the y-axis because of that shift to the right of 3. It's at 3. Right. It's been moved over 3 and up 4. That's the new graph. Right. It goes on forever in that direction. It goes forever down. If you put it in the calculator, look what it does. It stops it. It doesn't handle vertical lines. So when it gets to be almost vertical, it just stops graphing it. That is not the graph of a logarithm. I mean, that looks more like the graph of the square root function. That does start at a point and go to the right with a curve like that, right? That is not a logarithm. And if all you're doing is copying that, you miss the basic shape. So don't let the calculator fool you. It'll do that every time. Okay, so describe. We're not graphing, we're just describe the transformations in these. So what do you see in the first one? They just gave us the same graph, didn't they? That's theirs. Okay. So this is still the right 3, up 4. And how about this one? What do you do to graph when you multiply it by a number bigger than 1? Stretch. Stretch. Okay, that's logarithms. So, like I say, first thing we need to know that logarithms are inverses of exponentials. Then we got to know how to convert logarithm to exponential to logarithm. Then we got to know what the shape of the graph is, the particulars, asymptotes, intercepts, things like that, domain and range. And then we got to be able to move it around by adding and subtracting, putting minus signs in front, things like that. So, this 12 through 19 is convert exponential to logarithm. Just rearrange the numbers, right? The 46 to 53 is the reverse. They're all logarithms, just rewrite them as exponentials. These two are evaluates, right? And they're going to have different bases, I believe, than you could do with the calculator. So you're either going to use the calculator or do the set it equal to x, convert to an exponential. And then these here, the 40 to 43, are just describe the translations and transformations. That's it. Okay, and so finish writing that down. So I'm going to take it off that screen when you're done. Got it? Okay. So for the quiz, copy it down, do it as a take-home. Okay? Copy it down, do it as a take-home. You can refer to your book. Right? The first 3, use these 2 functions. Right? Remember what it is to add 2 functions and divide 2 functions. And for that one in particular, make sure you state the domain, because that's when domain starts to be an issue. Okay. And then remember, there was another operation, not like anything we've done before, which is compositions of functions. And so there's one like that too. All of these things have examples in the book that do exactly the same thing. Okay. These all come from section 6.6. 6, I can't write on that, 6.6, right? This one here is find the inverse. Okay. There's at least 2 different examples where they do it. Remember the steps were replace the f of x with a y, switch the x and the y, solve for y. Right, it's with that function right there. And then the last one, sketch the graph of a square root function which has been transformed by what you see. Make sure when you sketch the graph, it's easy to see the details of how it's been moved around, and you get the basic shape correct.